We are talking about inverse of an exponential function, continuing today, and we've talked about that. So some of this stuff is going to be a review. All right, so let's start off with this bridge. We're on page 109. All right, describe the domain and range of the function 2 to the x, which is what's graphed here. And we graphed this the other day. As far as the domain talking about x's, if you look, I'm hitting all these X's over here on the left. I'm going to keep going up and out right here on the right. So I'm going to hit every X. All right. There's not an X value you cannot put in that exponent spot. However, as far as our range, all right, here, do you see how this is staying above the x-axis? So here, we are going to be above the x-axis. So you can say y is greater than 0. It's not actually going to touch. It's going to run right close to. Or you can do this, 0 to infinity. All right. And we've looked at domain and range before. Okay. Now, let's revisit this writing inverse functions. Okay, so in unit 1, we talked about finding equation for the inverse. So if I have this right here, what are you supposed to do for the inverse? All right, you're supposed to switch your x and y's. So if that's y right there, x equals 2, y plus 6, and then divide by 3. And then we're supposed to solve for y. So here to solve for y, we would multiply by 3. So 3x equals 2, y plus 6. Some of you are going to want to distribute that 2, so why don't we do that? 2y plus 12. You could divide by 2 first if you would like. Now subtract 12 right here, and we get 3x minus 12 equals 2y. And then we divide by 2. All right, now the inverse could look like this right here. When I say 3 divided by 2, it's 3 halves and then x, and then negative 12 divided by 2 is a negative 6. So you can either leave it like this where my finger is, or you can leave it right there. Now, to always check your work on this to see if you did it correctly, remember, and I'm going to have to add this in, we can go to Desmos. All right. And let me do this right quick so we can see this at the same time. All right, so here, our original problem was 2 parentheses x plus 6, all right, divided by 3. All right, the one that we got was 3 halves x and then minus 6, like that. And remember, it looks like it reflects over the line y equals x. And when I zoom out, it does. All three intersect together, and the red does look like it reflects over the green to the blue. All right, and so forth. So we did it correctly. Now, let's go back up to this function right here, though. All right, so this is all of this right here describes 2 to the x. So f of x equals 2 to the x. Now, the other day we talked about the inverse of an exponential. Well, what is the inverse of an exponential? What do you remember? It's a log. So the inverse in this case of f is going to be, remember, log base 2 of x. All right. And remember when we plug it in, so let's go graph it right here. So we'll graph the original, so 2 raised to the x. And then here, log, remember that it's going to be underneath the keyboard. We go to functions and we scroll down. It's where it says calculus, but this log base, we put 2 and then we say x. All right. And if we put in y equals x in, doesn't it look like it reflected? All right. Well, let's talk about the domain and range here. Well, here, do you see that, okay, my x values, all right, it's not going past this y-axis. So my x's aren't ever going to be negative. Now, this goes all the way down here. But just like here on the x-axis, it never touched it. This isn't ever going to touch the y-axis. So our domain of this one is going to run from 0 to infinity, or x is greater than 0. All right. Now, our range, well, look, this keeps going all the way down to negative infinity. And then this, now it's going to go slow, but it's going to eventually go up and hit all the y values up. So this time, it's negative infinity to infinity. All right. Now, when I hit this, what do you notice? Do you notice that the domain and range actually flip-flops? So here it was negative infinity to infinity. Now the range is that. Okay, and then vice versa here for the domain and range. So anytime you have inverses, not only do they reflect over the line y equals x, but their domains and ranges also flip-flop. all right, as well. Okay, so flip over to activity 1 on page 110. All right, so I'm going to flip over. We're going to go to activity 1. All right, we were actually just talking about this for a second, so I'm just going to re-hit it again. This is 2 to the x. This is the graph. All right, don't forget. So here for the inverse, well, what do we do with inverses? Well, we switch our x and y. So instead of it being 0, 1, 1, 0. All right, instead of 1, 2, 2, 1. 8. So that's going to be 8, 3, and this is going to be 64, 6. And so let's go plot some of these. So 1, 0, all right, is now here. All right, 2, 1, 8, 3. Now I can't really graph that other one, but I can go like this. All right. And if I put in that line y equals x, which is at 1, 1, 2, 2, 3, 3, 4, 4, okay, all right there. Does it not look like it reflects over that line right there? And it does. It reflects over this line like that. Okay, so what type of function do we have here? All right, we have an exponential function. What did we say the inverse of it is? All right, it's a logarithmic. Okay, and that logarithmic function looks like this. So the inverse equals log base 2 of x. All right, so here we're just reviewing what we've got right here. All right, so we've done number 1 and number 2. We completed the table, we've found the inverse, we've graphed the inverse, and so forth. So let's move on to number 4 on the other side. It says, if f of 10 equals 10, 20, what is this right here? Well, just think about it for a second. This is talking about the inverse. So if this point is 10 and then 10, 24, well, then for the inverse, it's going to be 10, 24, and 10. So this, the inverse at 10, 24, is going to come out to be 10 as the answer. And we could graph that on the graph. However, that's a little high. All right. And so let's describe the domain in range. All right. So we just a little while ago described the domain. The domain of 2 to the x was negative infinity to infinity because we could plug in any x. And the range goes from 0 to infinity. All right. Now, as far as the inverse is log base 2 of x. And then the domain, remember, and the range actually swap. So this is going to be 0 infinity, and this is going to be negative infinity to infinity. All right, so we're just kind of reviewing some stuff that we had done from the warm-up, and I even added some extra stuff in. All right, let's move on to page 112, and we're going to look at activity 3. All right, so find the inverse of the following exponential functions. All right, so if we're finding the inverse, and this is some of the same stuff that we've done before, all right, think about solving for x as well. Our base is 10. Well, this is an exponential function. So the inverse of this, okay, our base is going to become the base of the log, and then it's x, like that. All right. So here, as far as this, and think about this for a second. You could do kind of like y if you wanted to. Here, think about whenever we do the inverse, we switch our x and y's. So here we would have x equals 3 to the y. Well, when we write it in logarithmic form, remember we do this. We take the log and we start at 3, and then we put x equals y. So this is the inverse right here. So that's what you can do with that. So again, now, here's the thing. I'm going to switch my x and y, so that's y right there. So x equals 2.5 to the y plus 8. All right, so here, think about solving for y. Well, the first thing I would do is subtract 8. All right, now, Okay, we got the y in the exponent spot. Well, how is that going to come down? It's going to come down because of a log. I'm going to flip-flop this around, all right, because I like to have the exponential part on the left-hand side. So I'm going to start here, and I'm going to put log. The base is going to be the subscript here. Then I'm going to go to x minus 8, all right, and I put that in parentheses, equals the exponent of y, and this is what the inverse is right here, okay? So we're going to do the same thing. All right, this is y. So switch my x and y's. X equals 12 times 7 to the y. All right, now you got to get 7 to the y by itself. So I'm going to divide by 12. So x divided by 12 equals 7 to the y. Now put the exponent spot on the left-hand side. All right, so now when I write this, all right, log, start at 7, that's my subscript. Then you put x over 12 right beside here. We can put that in parentheses if we want, equals the exponent of y. But really, this is the inverse. And that was the inverse of j. I should have probably wrote inverse of h on that one. This one should be inverse of g, like that. Okay, so that's what we can do with inverses. You switch your x and y's, and then we solve. But remember, when it's an exponential, it turns into a log. Just be careful, especially when we have things added and subtracted and stuff like that. All right, so here, let's find the inverse here. Let's do the same thing. There's our y. Okay, we're going to switch it. All right, now this is the base raised to an exponent. So this one's going to be a little bit different. Now I'm going to solve for y. So here we're going to do log base 2 of x equals, all right, and then the exponent is y minus 6. Now, y is not quite solved for yet. Well, what do we have to do? We have to add 6. Now, what happens is this log base 2 of x, the 6 is just added out to the side right there. It's not added like with x, kind of like this minus 8 right here. All right, and then this equals y, or the inverse of p. All right, now you could also do the 6 plus log base 2 of x. That's another way to write it. All right, as the inverse. All right, now there is a question down here, number 2. Andre claims that this can be written like this. Explain why this is true. All right, this is a little more advanced, but if you remember anything about exponentials, 2 to the x times, all right, here, if you ever have this, remember our exponents were added together. So here, I can take them apart, all right, and say 2 to the negative 6. And if you remember anything about negative exponents, that negative 6 could actually go down low and make 2 to the 6. So this is a little bit of an extension, if you remember, properties of exponents like that. All right, so we're going to look at a couple more problems, all right, but I have them on another sheet, so make sure you get that out. All right, so here we go. Get organized here. Let's look at number 1. All right. We're going back to these word problems, making sure that you understand them, all right, and can solve. As of 2022, the world population is 7.89 billion and growing at an annual rate of 0.9%. Write a function to represent the population in billions, p, after t years. Try to do it with the p and the t instead of x and y. All right, so if we're writing a function, this is growth. All right, here's our generic form right here. Does not say compounded, so I'm not using the ones with ends. I'm starting out with 7.89 billion. All right, 1 plus, now the percentage. Okay, take 0.9 and divide it by 100. You're going to get 0.009 when you throw it into the calculator. So 0.009. Now, instead of putting x, I'm going to put t. And this should equal p. You can also write this as p of t, like that in function notation. Now, how many years will it take for the population to reach 10 billion? Now, realize this is in billion. I didn't want to put all the zeros. You do not need to do that. Just realize your answer comes out as 10 billion. So here, or in billions, so 10 equals And I'm going to go ahead and add that together so it's like that. And remember solving this. You are welcome to divide by 7.89 if you would like, or just go straight to your calculator. Okay, one side equals 10. There's no x with it, so make sure you put y equals 7.89, whoops, that's a 2, 7.89. And then I do 1.009 raised to the x, like that. All right, zoom out. I can kind of see it looks like it's going to intersect. There we go. Sometimes these numbers can be really large, so be very careful. So 26.45. Okay, so 6 equals 26.45. So it's going to take that many years for the population to reach 10 billion. All right, now moving on. Number 2. Your iPhone costs $700 and depreciates at a rate of 12% each year. Write a function to represent the value of the iPhone, V, so the value, after t years, so V of t. All right, now this time, y equals a, 1 minus r to the t, or x, or whatever. It depreciates means you're taking away, you're minusing, you're going down. All right, so we're starting off with 700. 1 minus, now take 12 and divide by 100, and you should get 0.12 to the t. So here's our formula right here. Now, when will the phone be worth half its original value? Now, this time they didn't give us like a number, but they did say half. We got to take half of 700. Or 700 divided by 2. And what is that? If you throw it in a calculator, it's 350. So you want to know, when is this going to equal half right here? Whoops. Minus 0.12. All right, to the t. And now you're welcome to subtract that to get 0.88 right there. It's fine. Now, here, if you want to, you are welcome to plug this in. All right, the way it is. So y equals 350. Okay, 700. 1 minus 0.12 to the x. Okay, like that. Now, the problem is you're going to have to zoom out really large. Now, this one's not terrible, but I can find the intersection right here, 5.422. Now, another way you can start out by doing it is think about what we had to do a little bit earlier. Divide by 700, all right, and get that exponent by itself first. So this is going to give me 1/2 equals, or 0.5 equals 0.88 to the t. Now, what we were doing earlier, and I just want to extend this, all right, weren't we doing something earlier? And so this, when we write it, log of 0.88 of 1/2 equals t. So really, now I could plug in my calculator like this once I divide by the 700, and I get y equals 1/2. All right, and it's 0.88 raised to the x. All right, notice I can see it really quickly. And isn't it the same answer, 5.422? All right, now watch this. Remember, I just wrote it as a log. Okay, if you remember how to write it as a log, another way you could solve it is, okay, now we put the log in, log base. That's not what I wanted. All right, log base of 0.88 of 1/2. All right, do you notice we get the same answer right here, 5.422? All right, so t equals 5.422. All right, so it's going to take that many years to get to that value. All right, and I had multiple ways of solving it using my calculator. You can put it in terms of log and just plug it in to get the value, if you know how to do that. You can also just, once you write it, the equation, and plug that in, then you could just solve it using the calculator. So here we go. Peyton invests $1,000 into a bank account that accrues 4% interest compounded quarterly. Write a function. Now here, this is y equals a 1 plus r over n to the nt. You got to memorize your formulas. All right, so starting out with 1,000. Now, it's the account V of t. All right. 1 plus, now our rate is 4%. So 4 divided by 100 is 0.04. Okay, here quarterly. Well, quarterly means n equals 4. So I'm going to plug in divided by 4 right here. That's a 4 right there. Okay, and I'm going to plug in t. All right, so here we go. Right here. Now, how long will it take the count to double in value? Double means times 2. All right, so we're going to take 1,000 and we're going to times it by 2. So that's 2,000. So when is this going to equal it? All right, well here, you can simplify this by saying 1 plus, all right, 0.04 divided by 4. So I get 1.01 to the 4t, like that. Now, you can solve it. So I'm just going to solve it different ways. You can solve it here, all right, by saying y equals 2,000, all right, and then 1,000, 1.01 raised to the 4x. All right, I don't see it at first, so I had to do a lot of, there we go. I had to zoom out a lot. All right, that's the only disadvantage using these big numbers. And I can see that it's t equals 17.415. Well, let's see how else we can get it. You could divide by 1,000 first. And when I divide by 1,000 first, I get 2 equals this 1.01 4t. All right, so like watch this when I solve it. Y equals 2 and then 1.01 raised to the 4x. Look, it's actually a little easier to find the intersection. And isn't that the same answer that I got right here? Yep. So that's another way to do it. We can also write this in terms of log. All right, so if I flip this around, 1.01 to the 4t equals 2, so log base 1.01 of 2, because I'm going here to here, it equals 4t. Now, the last thing I would need to do is divide by 4. All right, so here, when I plug all that into my calculator, all right, so it was log base, so functions, scroll down, log base 1.01, okay, and then of 2, close my parentheses, and then take all of that and divide by 4. All right, and you'll notice it is the exact same answer. All right, to plug in. So we get the same thing, t still equals 17.415. All right, so we can use the method when we're solving these equations that we were doing earlier and putting it into log form. All right, number 4, last one here. A 500 milligram dose of penicillin has a half-life of 1 hour. That means every hour it takes half. At what percentage does the penicillin decay per hour? Okay, so let's think about this. I'm starting out with, now this one, you kind of want to just use a to the bx, all right? Now, you can say if its half-life is decaying at 50%, if you wanted to use those other formulas with percentage. But here, we're starting out with 500, and we're taking half, all right, to the x. All right, so let's think about for a second. So this is 250. All right. Well, here, let's think about it. It says at what percentage does penicillin decay per hour? Well, right here, this would be minus, think 1 minus r. Well, that equals 1/2. When I go and solve that, I get r to be 1/2 or 0.5. Well, when I change that to a percentage, when I multiply that by 100, 50%. So that's another way to figure out what it's decaying per hour. So if it's half-life, you're decaying 50% per hour. Now, the question is, when will there be 100 milligrams? All right, 100 milligrams, when we use this formula, is going to be like this. Okay, so remember, X stands for hours. All right. All right. So here we go. you can do everything that we're doing. I'm going to write it in log form. You can just graph this and find what x is. But here, I'm just going to divide by 500 just to show you how we put it in log form again. So I get 1/5 equals 1/2 to the x. All right, I'm going to flip this around, the exponential on this side, and it's going to be log base of 1/2 of 1/5 equals x. So no matter if you graphed it and found the intersection, you can also write it in terms of log. So when I plug this into my calculator, all right, I'm plugging this thing right here in, hit functions, scroll down here, log of 1/2, all right, and then scroll over, and then put 1/5 in. All right, and we realize that x equals 2.322 hours. It's going to take that many hours to get down to 100 milligrams. Now, I do want to recall on this how we get logs, just in case you like to use these. So to get log, we do alpha y equals. If I use my arrows and I scroll over 1, I want number 5 for log base. All right, so here, this is going to be 1/2, 1 divided by 2. All right, and then that's 1 divided by 5 right there. And there we go. We got the same answer that we just got on Desmos. All right, so don't recall your word problems. Make sure you know how to do that. You can solve them using Desmos, just finding intersections, or you can write them in log form. So we, again, practice log form, and remember that a log is the inverse of an exponential. And when we start talking about domain and range of an exponential, if I flip-flop the domain and range, that's going to be the domain and range of your log equation. All right. Thank you. And we pretty much have covered almost everything with logs for Math 3 and exponentials. So make sure you review over everything that we are doing and ask your teacher if you have any questions.